So okay, now we will see the determination of dissociation constant. Determination of dissociation constant. Now the dissociation constant is actually designated by symbol Ka. It's for acids, and Kb is for base, dissociation constant for a base. So acid for weak electrolyte such as acetic acid. So this is for ammonium hydroxide. It's a base, a weak base. So now how one can determine dissociation constant of a weak acid or weak base by using by measuring electrical conductance. So before we going on, we can measure it. Now let us formulate the mathematical requirement. Now that is actually based on the Oswald's dilution law. So first we should know Oswald's dilution law. So according to this law, so any weak electrolyte, so this law is applicable to an equilibrium, that is actually any weak electrolyte dissociates into ions only by a fraction to the total number of molecules Now we can take this statement, a weak electrolyte such as acetic acid. So this is a acetic acid, so it actually undergoes dissociations only by a fraction, acetate and H plus. Okay, now this fraction we call it as a degree of dissociations. That fraction we call it as alpha, that is degree of dissociation. Now what we are saying is that the Oswald actually pointed out that now we can apply the equilibrium. Now we can apply the law of mass action to this equilibrium. So after applying the equilibrium, now equilibrium constant we call it as Ka. Here acetate H plus, concentration of H plus divided by acetic acid. So this is an equilibrium. Now this equilibrium constant we call it as a dissociation constant. Okay. Now this is the concentration of acetate ion. This is the concentration of H plus. This undissociated molecules after gaining a certain equilibrium. Okay. Now suppose it happens that if 1 mole of the electrolyte or acid, 1 mole of the acid dissociated into ions or dissolved in a given solvent, it will undergo dissociations. Then it actually acquires an equilibrium. Now after that, after acquiring an equilibrium, so this is acid, it undergoes dissociation. Okay. Now after dissociations, it actually acquires an equilibrium. Now if it is 1 mole of the acid, so this is alpha number, actually dissociated by a fraction. That fraction we call it as alpha. Now a fraction of the amount of the acetic acid is actually dissociated, that is alpha. alpha. This is also alpha because same number will be dissociated. Now if it is 1 mole of the acid, that gives the concentration, so we need to multiply the concentrations here. So let's see, is the concentration, this is concentration C. Okay, so here it is alpha times is actually dissociated, the remaining is 1 minus alpha multiplied by C. You can substitute Ka is equal to acetate H plus divided by acetic acid, the concentration. Now acetate is actually alpha times C into alpha, so this is C into alpha into C into alpha divided by, so this is C into 1 minus alpha, so we will get C square alpha square divided by C into 1. Now C get cancelled, we'll get C alpha square 1 minus alpha, where C is a concentration. If suppose it happens that if 1 mole of the acid is dissolved in a solvent of a volume V, now concentration will be 1 by V liter per mole. Now this is concentration. Now we have dissolved 1 mole of the acid is dissolved in a certain solvent of a volume V. Now the concentration will be 1 by V liter per mole. Now we can substitute that Ka C is equal to 1 by V alpha square 1 minus alpha to V. Now here we can derive a mathematical equations. Now alpha is very small. Alpha is very small number, very small number compared to 1. So it is in the power of 10 power minus 5 minus 4. So we can neglect 1 is greater than alpha. So we can neglect alpha. So if you neglect alpha, Ka is equal to, in comparison with what we are neglecting, alpha square V. Sorry, alpha. So it is alpha square divided by V. Now or Ka, if it is 1 by V is equal to C alpha square C. Now Ka alpha is equal to Ka by C square root. Now here alpha is equal to Ka into V square root. Now what we can derive here is that the degree of dissociation is directly proportional to the square of volume. So here the degree of dissociation is directly proportional, inversely proportional to the square root of concentration. So this is what we have derived with respect to the degree of dissociations in connections with the dissociation constant. Ka alpha square C to 1 minus alpha, or Ka alpha square 1 minus alpha into V. Now we know that what is alpha. Alpha is the degree of dissociations. In terms of electrical conductance, alpha is equal to lambda V, lambda infinity is the equivalent conductance at a particular dilutions. This is equivalent conductance at a infinite dilutions. Now we just substitute there. We can substitute there, we will get, so alpha square lambda infinity whole square divided by 1 minus lambda v lambda infinity into v. So we can solve these equations. If we solve these equations, we will get lambda v square lambda infinity square, this is lambda infinity minus lambda v divided by lambda infinity into v. So Ka is equal to, if you take it to the upper side, lambda infinity square into lambda infinity minus lambda v into v. So lambda infinity get cancelled. One of the equations, what is left is lambda v square divided by lambda infinity minus lambda v into v. So this is the expression for the dissociation constant in terms of equivalent conductance at a particular dilutions and equivalent conductance at infinite dilutions. V is the volume of the solutions. Now this is how one can determine the dissociation constant by measuring the electrical conductance, thereby equivalent conductance. Now lambda v directly we can measure lambda v at a particular dilutions. Lambda infinity can be measured if it is acetic acid, lambda infinity of acetic acid if you want. So we can get this from lambda infinity, this is a weak acid, lambda infinity of NaCl, lambda infinity of sodium acetate, lambda infinity of HCl, because the electrical equivalent conductance for a strong electrolyte it will be easily determined. So HCl, lambda infinity of sodium acetate in NaCl. So this is experimentally determined. By determining experimentally, we can calculate this lambda infinity. This is experimentally determined quantity. So just apply this equation to there, we will get Ka. So lambda infinity can be determined by using Kv into 1000 divided by C. So Kv is the specific conductance at a particular dilutions, that is kappa. So now another concept is actually conductometric titration. Conductometric titration. So the titrations involves the measurement of conductance. So conductometric titration nothing but the titration involves the measurement of conductance as a function of volume. We call it as conductometric titration. So here the conductometric titrations can be classified as so depending upon the analyte and the titrant. So based on the analyte and titrant, so it can be conductometric titrations will be different types. The first type is acid base titration, acid base precipitation. So we don't have precipitation titrations, only we have acid base in the syllabus. So we can learn these precipitations in some other classes or some other videos. So acid base titration. So the first type is actually strong acid versus strong base. Acid versus strong base. So for example HCl versus NaOH. HCl versus NaOH. Now HCl is also electrolyte, NaOH is also strong electrolyte, they will conduct. If you see this equation, now to carry this conductometric, before we going the actual reactions, what happens in the conductometric titrations. So in the out we will carry the conductometric titration by using a conductometer, so which actually displays the conductance of a solutions, and using a conductivity bridge or conductivity meter and conductivity cell by dipping the conductivity cell. So usually the analyte is taken as 50 ml. 50 ml of the analyte is taken, and we will dip the conductivity cell to the 50 ml, say for example HCl, and the concentration of this will be maintained 0.01 normal, and NaOH will be maintained at 0.1 normal. So we can look at the difference. So the titrant should be 10 times greater than the analyte. Why? Because this is maintained. So because in order to minimize the volume change, this is maintained because in order to minimize the volume change. So because we know that as the volume increases, it will seriously affect the conductance of the ions. That is why now the increment, for every increment we are actually measuring. So maybe the increment is 0.5 ml. Now we are taking 50 ml. Now that overall addition is 50.5 ml. So in considerations of this 50 ml, the increase in the 0.5 ml doesn't affect the conductance. Now we can directly take the observed conductance without doing any mathematical manipulation. Now in this case, strong acid versus strong base, HCl plus NaOH will get NaCl and water. So this is the reaction. Now HCl is at it has H plus and Cl minus, and so after adding, so this is 50 ml. After adding NaOH 0.5 ml, now the HCl will be converted into NaCl. Now the HCl will be converted into NaCl. H plus will goes to a non-electrolyte. It goes to a non-electrolyte medium. So only Cl minus will goes to the electrolytic medium. So only the Cl minus will be survive. Now the H plus is replaced with Na plus. Now in comparison with H plus and Na plus, what will happen to the conductance? So the overall reaction is that the H plus is replaced with Na plus. Cl minus is survived. Now H plus is fastly moving cation. It is a fastly moving cation because of its smaller size. It has a smaller size. This is a fastly moving cation, and this is a slow moving cation. If it is a fast moving, the conductance is more. If it is a slow moving, conductance is less. Now during the course of the titration, a fastly moving cation is replaced with a slow moving cation. So therefore initially the conductance is very high. As it is replaced with Na plus, the conductance goes on decreases. The conductance is decreases. Now that can be seen by plotting a graph. So we can run it iterations up to 20 ml. Now this is volume of NaOH. This is conductance in Simon or millisimon, whatever it may be, millisimon. So initially the conductance is very huge. Now it will decreases and then it will increases. Now this is due to the replacement of H plus with Na plus. This is due to HCl, and again the conductance increases. That is due to unreacted NaOH. The conductance goes on decreases until all the H plus is replaced with Na plus. So once it is the deflection point, once the deflection or equivalence point is reached, after that the conductance is goes on increases because all the H plus is used up. Now this is the equivalence point. Now this increase is due to the excess of NaOH, that's unreacted NaOH. This is unreacted. Now similarly another titration, that is weak acid versus strong base. So the weak acid is actually acetic acid plus strong base is NaOH. You will get sodium acetate plus H2O. Okay, now acetic acid is a poor electrolyte. It's a poor electrolyte because of poorly dissociations. This is strong electrolyte and this is also strong electrolyte. So because of the poor electrolyte, it doesn't dissociate completely. It doesn't have ions to produce conductance. So therefore, after addition of a strong electrolyte and due to the formation of a strong electrolyte, this dissociates completely. Now initial stage of the titration, the conductance actually slowly, it has some conductance slowly increases. This is due to the formation of sodium acetate. Once all the acetic acid is converted to sodium acetate, after that there is a sleep increases. This is due to unreacted NaOH because NaOH is strong electrolyte compared to sodium acetate, and this is due to the formation of sodium acetate, CH3COONA, and this we call it as equivalence point. That is the volume of NaOH required to neutralize acetic acid, this value. So this is conductance. So this is with weak acid versus strong base.